Planetarium and Science Visualization, Ryan Wyatt.
Well, thank you, Bing, and it's a great pleasure to introduce tonight's speaker. Dr. Risa Wechsler is the director of the Kavli Institute for Particle Astrophysics and Cosmology. The very, very small and the very, very big combined in one short name. She started out her academic career at MIT for her undergraduate, and then went on to UC Santa Cruz for her graduate work. Spent a few years in the Midwest at the University of Michigan and University of Chicago before returning to Stanford. Her work focuses on mapping the large-scale structure of the universe to help us understand, as you might guess from tonight's title, the nature of dark matter and dark energy in the universe. And I have to say, it always warms my heart when a speaker really dives into the dome aspect of the presentation. And so I want to thank Dr. Wechsler for doing that in collaboration with Matthew Wren, who's up at the top of the dome. We're going to have a very immersive presentation tonight. And although I think Dr. Wechsler will make her opening comments from here at the front and do Q&A at the end, from up here, she'll be up in the pilot's booth, helping make sure our trajectory through the universe goes smoothly. So please welcome Dr. Risa Wechsler.
Thank you. It's a real pleasure to be here, and as Ryan said, I am going to talk to you about the parts of the universe that we cannot see. I'm interested in the really big questions about the universe, how the universe formed, and what it's made of, and I hope to give you a couple of clues about those two questions tonight, using everything from the tiniest galaxies to the biggest maps that we can possibly make. So I am going to, as Ryan said, I'm going to jump to the back of the room. And while I do that, let's maybe we can go ahead and bring up the first image so I know what we're doing here. So if you're interested in learning about how the universe formed, the first thing you might do is look up. And I'll wait for these folks to get a seat. Okay, and so hopefully some of you have been able to look up at a dark night sky and see this spectacular galaxy, the Milky Way, which is the galaxy that we live in. The Milky Way is a pretty normal size galaxy. It's got about 100 billion stars in it. And we can learn a lot about how our universe works from looking at just this one galaxy. But if you really want to understand what the universe is made of, you might want to go a little bit deeper. So until quite recently, this was the deepest image. We're getting there. This was the deepest image of the universe ever taken, if we can get to Hubble. There we go. So this is the Hubble Ultra Deep Field, which until about 6 months ago was the deepest image ever taken of the universe. And in this one tiny patch of sky, which was actually chosen to be basically a blank patch of sky, you get about 10,000 galaxies. And if you extrapolate that to, roughly the scale of the whole universe, you get a number that's maybe close to 1 trillion galaxies. So that sounds like a lot. Maybe the universe is made of galaxies. But sometimes there's more to the universe than meets the eye. And just to give you an example of the fact that sometimes there are things that you can't see, let's come back close to home and just think about the Earth. And think about what happens when you look at the Earth in the daytime or if you look at the Earth at night. You see actually quite different things. So if all you could see of the Earth was these lights, you might be missing a lot. You might be missing a lot of where the mass is on Earth. If you go over to, say, the Rocky Mountains or something like that, you might not see too much. You can see maybe where you can see, I can see Miami there. I can see New York. I can maybe see San Francisco there. And then I see a whole bunch of nothingness there in the middle. So the point of this example is that, sometimes there is mass where you don't see light. So this answer to the question of what the universe is made of, I'm going to tell you the answer now, and then tell you the things that we don't know about this. So you and I are made of, some carbon, oxygen, hydrogen, helium, those kinds of things. And most of the stars and the galaxies in the universe are also made of those things. Getting to the, no, we're going to that one. Okay, there we go. So here's a galaxy made of basically the same things you and I are, but it turns out that most of the rest of the universe is made of something different. So everything in the periodic table is made, only makes up about 5% of the universe. That's what's called normal matter here. In this pie chart, about 25% is dark matter, and the other 70% is dark energy. Now, we don't know actually what either of these things are, but we know a lot about how they behave in the universe on large scales. So in this lecture, I'm mostly going to be talking about the dark matter piece, but we'll touch on dark energy just a little bit. So in order to tell you a little bit about how we know that the universe is not made mostly of atoms, not made of the same things that you and I are, I'm going to go back in time. And so that's what we're doing now, starting to go back in time. The beautiful thing about the universe is that because light travels a finite speed, every time you look at any distance away from us, you are looking farther and farther back in time. So now in this image, we've gone to a field of galaxies. Every point in this current image that you're seeing is a galaxy. And one thing before we move on, I want to just take a look here and notice that the galaxies are not distributed randomly. So you do see some blank spots where there's nothing, where it's just totally dark. That's actually just where the telescopes didn't look yet. But the structure you see in this distribution is real. These are real galaxies whose positions have been mapped by the previous generation of surveys, primarily by a survey called the Sloan Digital Sky Survey. And those galaxies, those points that you still see fluffy there in the middle, reach out about 5, maybe 7 billion light years in the past. And now we've gone all the way back to the beginning. I can turn off the galaxies for a second there. So if we turn off the galaxies, we're now looking at light from just about 400,000 years after the Big Bang. So this is something called the cosmic microwave background. And this light is the light that was emitted very early in the universe. The key thing you should know about the history of the universe is that it was hotter in the past. It's been cooling off because it's been expanding. And it was hot, and it was also very, very smooth. So it was almost the same temperature everywhere. But if you, do we have an image of this or someplace where you can see the spots? Maybe not. Okay, so this cosmic microwave background was almost the same in every direction, but there were little places that maybe you can see here that were a little bit underdense and a little bit overdense. That is actually a beautiful input to the simulations that we can do to try to understand what happened next. So now we're going to go forward in time, but we're going to go forward in time using a computer. And the things that we just saw were the initial conditions. So this is the initial conditions of this simulation, and the physics in this simulation is gravity. So the main thing that we are simulating here is matter, and most of the matter in the universe is dark, so most of what we are looking at here is dark matter. This movie spans about 13 billion years, and you can see that in the first few seconds of the movie, which were, the first billion years or so, the movie started out very, very smooth. There wasn't a lot of structure. And as the movie evolves, gravity works its magic. Anywhere where there was a little bit of stuff to start with, we get a lot more stuff pulling it together. And this is really a view of how structure forms in the universe over time. Those bright spots in this movie are where the galaxies form. And this is a key part of the story. Galaxies can only form when the universe gets dense enough that gas can cool and start to form stars. And so what you see in this movie is that there are regions of the universe that are quite dense, have a lot of dark matter, and that's where you start to get galaxies. You could also see in this movie that there was a lot happening. Starts out pretty quiet, and a lot happens as these galaxies merge and grow over time. So this process is a lot of what I study, and the movie that you saw here is a picture of, we can go forward. The movie that we saw here was a movie where the conditions were very much like our universe. And what I want to show you in these two sort of toy models side by side is that we can simulate lots of different kinds of universes, okay? So these are two example universes that I can simulate in a computer. In this particular case, they have different amounts of dark matter. So what I want you to notice as you look at these two movies side by side is that they start out looking kind of similar, and by the end, they look more different, okay? And this difference, you can see, would translate into a difference in how galaxies are distributed in the universe. So if we're able to make these predictions for different amounts of dark matter, then we can actually compare those predictions to the kinds of maps that we make and see which ones look more like the real universe. Let's go on to the next one. In the next one, I want to give you an example of, that's not it. There we go. So these are two other sort of toy simulations, and in one of them, I took away most of the dark matter. And I did that to indicate that actually, if you don't have very much dark matter, so that's the one on the right, is the one without a lot of dark matter, just a tiny, tiny bit. The one on the left has sort of roughly the amount of dark matter we think exists in our universe. And the main thing I want you to notice is that in the one on the right, not very much happens. It's kind of boring. So whereas in the one on the left, it was actually quite active. Again, these movies are just about 10 seconds. I don't know, we've got some strange artifacts, but that's okay. The main thing is that there's a lot happening in the one on the left, not a lot happening in the one on the right. Okay, so what we can do, actually, I think we're going to just go to that halo image. Okay, so this is just a zoom in on the universe that looks a lot like the one we think we live in. And the thing I want you to notice here, this is a big zoom in of one clump of dark matter, which we call a dark matter halo because it surrounds the galaxies. So you should think of the yellow stuff here as the galaxy, the black stuff around it as the dark matter. And so by actually studying the distribution of these galaxies and how they're distributed with dark matter, we can learn a lot about these. a lot about what dark matter is. Let me give you one more example, going to the gravitational lens. Let me give you one more example of why we think dark matter exists from looking at observations of the sky. So this is a image of a gravitational lens. So this is a large galaxy cluster, and there's two things going on in this cluster. In this universe, you each have very large eyes that are separated widely apart so that you can see this gravitational lens. But the key thing that's happening here is this is a very, very massive galaxy cluster with thousands of galaxies in it. It's probably 1,000 times more massive than the mass of the Milky Way. And two things happen because it's so massive. The first is all of that mass holds the galaxies together. So those galaxies are spinning around the center very fast, except for something just happened. Does anyone want to guess what just happened? Something just happened in this movie, and it started to look different. That didn't quite work. Paused. Okay. All right. Well, it should have happened. All right. So there were two things I wanted you to notice in that movie. One is that there was so much mass there that the galaxies are getting stretched. And the second is that the galaxies were rotating really fast. So midway through the movie, should have happened that the dark matter actually just got turned off. And because it got turned off, the galaxies can no longer be held together, and you no longer see this gravitational lensing effect. So that lensing effect is similar to a lens, like you have a wine glass or something, and you look how light is bent around it. Similar thing is happening here, and that only happens because gravity bends the light when there's a lot of mass there. So it's a really good clue that you have more mass in this system than you can see. Okay, let's move on. So based on lots of lines of evidence, including the two that I just told you, we think about 85% of the mass in the universe is dark matter, about 15% is visible matter. So these two things together still only make up about 30% of the total energy in the universe, and the rest is this thing called dark energy, which is not matter at all. But, some of you have probably heard of these things on the left-hand side: protons, neutrons, quarks, neutrinos, photons, electrons. These are all things that we've been able to measure them. We know they exist. We can measure their properties. We can measure their masses. We can measure what happens when they interact with each other. And so we know a lot about that visible matter. The dark matter side, we can measure how much there is, and I'll tell you in a few minutes how we measure where it is, but we really don't know what it is. So these examples that you're seeing here are just possibilities for what dark matter might be. We don't know if it actually is any of these things. Particle physicists are really good at coming up with creative ideas. So this list of 6 things is probably a very incomplete list of the possibilities for dark matter. Okay, so one thing we might try to do is look for interactions between dark matter and normal matter. That would be a great way to figure out what it's doing. So we have some ways to do that actually right here on Earth. So one thing we can do is build a really, really big detector. And this is an example of a detector that is actually in South Dakota. Basically, you want to look for a place that's deep underground, so it's really convenient to put it in a mine. And so this place, the Homestake Mine in South Dakota, turns out to be one of the best places in the world to put big dark matter experiments. And in this case, are we going to fly into it or not? Okay. So in this case, we have a dark matter detector, and what we want to do with that detector is just wait for, we want to put a lot of normal matter in one place, and then just wait for the dark matter to strike. Okay, let's go to the next possibility, which is Atlas, if we can. Okay, so this is another way we might detect dark matter, and that is we could smash normal matter into other particles of normal matter at very high velocity. And it could be that if you smash normal matter into other normal matter at high enough velocity, that you would create new particles. Very likely you would create new particles, and could be that some of those particles would be dark matter. So this is an image of the Atlas experiment at CERN, which I believe is currently the largest experiment ever built. And they have been, for the last several years, smashing things into each other at high velocity and trying to see if they find dark matter. So far, they have not. They actually did find one new particle called the Higgs, but they have not yet found dark matter. There still is a chance that they might. Okay, let's go on. There's one other possibility. So the first possibility we discussed was dark matter runs into normal matter and we see something. The second possibility is we smash normal matter into normal matter and we create something. The other possibility is that dark matter and dark matter could run into each other and create very high energy photons. And those photons are high energy, so they would be in the gamma ray. About 13 years ago, we launched this satellite. It was actually, the detector was built at SLAC in Menlo Park. And this satellite, the Fermi Gamma Ray Space Satellite, has been looking for gamma rays in the entire sky for the last 13 years. And they were also really hopeful that they would find dark matter. So far, they did not. But we learned a lot from these experiments about what dark matter isn't. So let's go to that constraints plot for a minute. The crazy thing about dark matter is that we know how much there is. So you give me a unit of space, I can tell you how much dark matter is in there. But I don't know what it is, and I don't know what it is like by a dramatic amount. I don't know the mass of the dark matter particle by 90 orders of magnitude. So it could be as massive as 30 times the mass of the sun, or it could be a billion, trillion, I think, times smaller than the mass of an electron. Okay, so it's about 90 orders of magnitude that dark matter could be. Actually, we do know that it's not smaller or larger than those, and those limits come from different kinds of astrophysical measurements. Sometimes, pretty much any time I talk about dark matter, people say, well, why haven't you found it yet? And I hope this plot will give you a little bit of a clue why we haven't found it yet. Most of those searches, including all of those 3 examples that I just gave you of ways to look for dark matter, have been in about 3 orders of magnitude of this 90 order of magnitude regime. And in fact, they haven't even covered all of that 3 orders of magnitude. I mean, the star that I indicated there is pretty schematic, but the basic idea is that even in that range, we haven't even covered all of the possibilities. So that's great. Let's go back to the Hubble Ultra Deep Field. I'm bringing you back to this image because the rest of the talk, what I want to tell you about is the fact that I think one of the best ways to find dark matter and actually to learn more about what it is, even its mass, is by looking in the sky. So we actually want to do both of these things. We want to be able to find it here on Earth and measure its properties, and we want to be able to measure those properties in the sky. So I'm going to tell you some of the ways we do that. So let's go to the dark energy survey. So this is a 4-meter telescope, sort of a just kind of modest sized telescope on a mountain in Chile. This is called the Dark Energy Camera, and for several years it's been doing a survey called the Dark Energy Survey. Its primary goal was actually to measure the properties of dark energy. But it's a really nice telescope. We built a new camera for this telescope, and we were able to do several things with it. So one of the things we were able to do is use gravitational lensing to make a map. Do we have the mass map? Okay. Okay, so we surveyed about 1/8 of the sky. I don't know if this image is working, but we surveyed about 1/8 of the sky. That's an example of the region that we surveyed in contrast to the Milky Way there, right? So this is just a projection of the sky. And what we were able to do is use 100 million galaxies. So we mapped out 100 million galaxies over 1/8 of the sky, and we actually made a map of where the dark matter is. By looking at how that evolves, we're able to learn also about the nature of dark matter. But this map is the biggest map made yet of where the dark matter is in the universe. And do we have the other plot or just this one? Okay. So the main thing here is that we actually, those contours that you see there are actually looking at the universe about 5 billion years ago where there is more or less dark matter. And now, if you remember one of those movies that I showed you, let's go back to that movie, yeah, that one. Great. Remember this little side-by-side comparison that I showed you, this schematic side-by-side comparison that showed you, if you have more or less dark matter, the universe is going to end up more or less clumpy. So by making that map of the universe, we're actually able to test what are the fundamental properties of the universe and really understand better what it's made of. Okay, so that's not the only thing we can do with this survey. The other really interesting thing, so I told you that we don't know what kind of dark matter there is in the universe. And let's stay on that one for a minute. This is an example of one galaxy like the Milky Way and the dark matter that surrounds it in two different models where the dark matter has different properties. So in the one on the right, the dark matter is what we call cold. So that means it's a particle that actually travels relatively slow with respect to the speed of light. In the image on the left, the dark matter is what we call warm. And that means it's a particle that travels pretty fast. The neutrino is an example of hot dark matter because it travels basically at the speed of light. Warm dark matter would be kind of somewhere in between, not quite the speed of light, but much faster than this cold one. And a consequence of moving fast is you see that on the right, there's lots and lots of little clumps. Dark matter is really clustered in that one on the right, whereas in the one on the left, there's not that many clumps. So let's see if we can test which one of these models actually looks like our universe. So in those clumps, we would actually expect to find galaxies. Do we have those? No? Okay. Okay, well let's just move on to okay, so we're back to the Milky Way. This is great. So how many of you have looked at the Milky Way from the southern hemisphere? Have any of you looked at the Milky Way from the southern hemisphere? Let's go ahead and pretend we're in the southern hemisphere and see what we can see. Hopefully. There we go. Maybe. Where are they? They're somewhere. Oh, there's one. Let's bring him up. Yay! These are two of my very favorite galaxies. So these galaxies are called the Large Magellanic Cloud and the Small Magellanic Cloud. These galaxies are actually galaxies that you can see even without a telescope if you live in the southern hemisphere or if you visit the southern hemisphere and have a dark night. So these galaxies they look really big on the sky because they are very, very close to us. And By very close, what I mean is that they are actually gravitationally bound to the Milky Way. So they're not within the stars of the Milky Way, but they are within the clump of dark matter, the so-called dark matter halo, that surrounds the Milky Way. And the Large Magellanic Cloud is the largest of these so-called satellite galaxies. The Small Magellanic Cloud is the next largest. Turns out the Large Magellanic Cloud, one of the things, I've been having a lot of fun with this galaxy recently because it's an interesting one. It seems that it was just brought into the Milky Way about 1 billion years ago, which is relatively recent, right? Because the Milky Way is maybe 12, 13 billion years old. So it's a relative newcomer. So these are the ones you can see with your eyes. And in fact, although they're named after Magellan, they were identified much, much earlier than that by many by Aboriginal societies in Australia and several other cultures. Okay, so let's go to those other satellites. About 20 years ago, we knew actually not just about those two, but from detailed measurements, we knew of about 11 satellite galaxies around the Milky Way. Okay, I don't know what we're doing with the Earth here, but in any case, those little yellow blobs are representing the additional satellites that we had identified before the modern era of survey astronomy, essentially using photographic plates. And the next thing that happened was the Sloan Digital Sky Survey, which had a camera which is about 120 megapixels, right? So that's about 10 times your iPhone. And the Dark Energy Survey, which has about 520 megapixels, okay? And that Dark Energy Survey camera, which is the same thing, the same camera that was really designed to make the very, very largest maps of the universe, mapping 1/8 of the sky. It turns out if you want to find the tiniest things in the universe, it is also good to map a lot of sky because the tiny things are relatively nearby and thus they look really big on the sky. So with that instrument, you can do something that you weren't able to do before. And let's look at that dwarf detection slide. No, that one. There we go. Okay, so why is this hard to find these satellite galaxies? It's hard because they're really, really tiny. So the smallest galaxy that we have now detected has about 300 stars. Now remember that I told you that the Milky Way has something like a few hundred billion stars. So a few hundred is very, very small. And not only is it a very small number of stars, they're very nearby, and so they're big on the sky. And so the image on the left is what you would see if you tried to look at this place where we now know there is a galaxy. You basically wouldn't see anything, you'll just see a field of stars. Most of the stars in that image are not stars in the galaxy of interest, they're actually stars in the Milky Way, which you can't tell apart. But if you have a big camera, like the one I told you about, you can take regular images in many colors, and you can actually start to distinguish these galaxies. And so that's what we see in the one on the right. And the amazing thing is just in the last 10 years or so, we have detected almost 60 of these galaxies. So we can go to the next one. Okay, so all of these galaxies, almost 60 of these galaxies are now actually, we've measured these things, and they are surrounding the Milky Way. And there we go. So you can imagine that there's a big clump of dark matter around the Milky Way, and these galaxies, some of them extremely tiny, are surrounding our own galaxy. The way we know that they are galaxies and not just, clumps of 300 stars is that we can also measure the motions of the stars in those galaxies. And when we measure the motions of those stars in the galaxies, we find that they're moving as if they had like 100 million times the mass of the sun instead of 300. So that's kind of weird, and that is indicating that these galaxies have lots and lots of dark matter. They're just chock full of dark matter compared to the amount of stars. But the other thing is that we found a lot of them. So let's go to that image of the halo again. The CDM. No, the CDM. That one. Okay, so you remember seeing a picture like this. So the one on the left is just looking at the dark matter. The one on the right is what we would actually see if some of those clumps of dark matter had stars in them. Okay? And, the Milky Way is schematically in the middle there. Lots of those clumps are going to light up and have stars. And, of course, that's the part we can see. Let's skip this one and just go to that one. Okay, so now back to this image where, remember, this was an image of two different kinds of dark matter. One that was moving fast and one that was moving slow. And what you can see is that they have very different numbers of clumps. So now that we've actually found a whole bunch of these clumps, we can tell you that the one on the left does not match our universe. Okay, so this is an example of how you can use these galaxies that just have 300 stars, these tiny, tiny things, and use them to learn about the nature of dark matter. And if we go back to that limit plot, there we go. If we go back to this plot, you remember these 90 orders of magnitude for the possible dark matter mass. Just by looking at these tiny galaxies, we can actually put new limits in this space. And it's a little bit complex to explain why the limits are in these different places, but the one that you see right in the middle, the one that says new limits in the middle there, that is basically saying that dark matter can't be too warm. There's a separate limit, which is on the far left, which is saying that dark matter can't be too what we call fuzzy. That's kind of a funny word, but it basically means there's a kind of dark matter called an axion, in which if the dark matter particle is very, very light, it actually behaves like a wave. And if the wavelength of that dark matter is large enough, it would actually be the size of those tiny galaxies, and it would totally erase them. So by the fact that they exist, we're able to put all of these interesting limits on what dark matter isn't. So we still don't know what dark matter is, but we know a lot more about what it isn't. Okay, let's go to the gravitational lens. So these tiny galaxies are one way to look for what dark matter is. An even cooler way would be if you could actually find the dark matter halos, these really tiny clumps of dark matter that are so tiny that they don't have any light at all. And one way to do that is by looking at gravitational lenses. So this is an image taken with the ALMA telescope. It's a radio telescope. And what you see, this curved orange band here, is light from a very distant galaxy, one galaxy that has been distorted by so much mass in the middle. And if this central galaxy had substructure in it, clumps of dark matter that are very small, it actually changes what this lens looks like. And so in this case, we were actually able to detect a clump of dark matter that was about 1 billion solar masses. What's really exciting to me is that in the next 5 years or so, we might even be able to detect a much smaller clump of dark matter, which would tell us that there's clumps of dark matter below the limit where you can form galaxies, clumps of dark matter that have no stars at all. And that would be an amazing verification of these ideas. So one way to do this is with new instruments. So one instrument that you may have heard of recently is the most recent space telescope. This is the JWST. It was launched last Christmas. And it is a spectacular instrument. It's a 6.5 meter infrared telescope in space. It's already detected just mind-blowing things every day. I'm seeing new images from this telescope. But those of you who pay attention to the astronomy news may have seen one of these first light images. So this is an image. This was one of the first ones that was released. This, similar to the other image we saw from ALMA, is a gravitational lens. And you can tell it's a gravitational lens because there's so much weird stuff happening. So if you look at some of the galaxies, they don't look like normal galaxies. They look really strangely stretched out. And in fact, is there a laser pointer? Let's see if I can. Maybe? Okay. Can you guys see that? Okay, so here's a cool example here. This galaxy here, this thing here is actually the same galaxy as this thing here. And this thing here, over here, is actually the same galaxy as this thing over here. So this is such a strong lens that it not only stretches the galaxies, it actually creates multiple images of the galaxies. Okay, so this is really cool for two reasons. One is that it provides a new way to find the clumps of dark matter that we otherwise couldn't see because they distort these tiny little arcs in interesting and predictable ways. It's quite hard to do. In fact, this is something my team is working quite actively on with machine learning techniques because we're trying to use these kinds of images to infer the little things that might be distorting them. But the other thing that's really cool about gravitational lenses is that they magnify the things behind them. And JWST is famous for being able to look farther back in time than we have ever been able to look before. But it's even better if you have a magnifying glass that basically enables you to look even further back. So let's go to, do we have that one other image? Great. So this is a brand new image taken from JWST. It's a truly spectacular image. Like you can zoom in like 5 more orders of magnitude, which we're not going to be able to do right now. But the main idea here is they pointed at a well-known galaxy cluster, which, because it's got a lot of dark matter, is a really good lens. And that might enable us to look for dark matter perturbations, but it also magnifies things. And this image is actually now, I believe, if we take the lensing into account, the deepest image of the universe that has ever been taken so far. Brand new image taken from JWST. Okay, I want to say a little bit more about the maps of the universe. Actually, before I do that, so in the last few minutes, I was telling you about the Milky Way itself, okay? And the Milky Way, as I said, so far we know of about 60 galaxies in the Milky Way. The most massive one is the LMC. But it'd be really nice to be able to find more of those and to put the Milky Way into context. So let's go to that simulation. So in order to put the Milky Way into context, you want to be able to do lots and lots of simulations. This is just an example of 25 different simulations that were done by my team. Maybe let's just watch it one more time. And the main point of showing you this is to show you that there's a lot of diversity in what happens in different kinds of dark matter halos. So you want to be able to study lots of these things at once, and you want to do that so that you can try to understand how our own galaxy, the Milky Way, fits into the broader picture. The other thing that you can do is try to study satellites in other systems. So let's just look at this example. So the Milky Way is the only galaxy in the universe where we can see 60 satellites. Our friend, nearby neighbor, M31, sometimes known as Andromeda, we've measured about 25 satellites. I've been working on a really fun project over the last 5 to 6 years called the Saga Survey, where we're tried to find 100 galaxies that look very similar to the Milky Way and identify as many of their galaxies, their satellite galaxies, as we could. And we've actually found about 380 satellite galaxies around sort of siblings of the Milky Way in that survey so far. And that's going to help us put the Milky Way into better context. Okay, another way to put the Milky Way into context is do even bigger surveys. So I'm going to tell you now about a few things that are coming up next. So this telescope is the DESI. It's called DESI. Actually, the telescope is called the Mail telescope. The instrument is called DESI, stands for Dark Energy Spectroscopic Instrument. This is actually a twin to the telescope that you saw that the dark energy camera was on. This one is at Kitt Peak in Arizona. It's also a 4-meter telescope. But the special thing about this telescope is that it doesn't have a big camera, but it has instead a big spectrograph. And for the first time on any telescope so far, it has 5,000 fibers. We don't have that movie, right? Okay. So this guy has 5,000 little robots that are able to position themselves on galaxies that have been identified and actually find out how far away they are. So it's able not just to map where the galaxies are on the sky, but how far away they are. So to really make a 3D map of the universe. And let's go to that first version of the map. So just to give you a feeling for how much better we're going to be able to map the universe with this instrument than before, the top is what we were able to do with the previous telescope, the Sloan Digital Sky Survey. The bottom is what we're able to do with this new instrument. This is just looking at a tiny piece of sky. So we're actually going to make this map over 1/3 of the sky. And this is a really exciting project for me because I helped to get it funded and get off the ground and planned what actual survey it would do. What's mind-blowing is we started taking data just a little over a year ago, and we already have more galaxies, more spectra of galaxies than have ever been taken by all other instruments combined. We've got about 18 million spectra of galaxies. And we should find a lot of these new tiny ones, but we also will be able to make really beautiful maps of the universe that tell us how the universe is expanding. Okay, the next thing coming is a telescope called the Vera Rubin Observatory. And let's go ahead and go to that. So the Vera Rubin Observatory it has the biggest camera that has ever been built. It's a 3.2 gigapixel camera. So in comparison to that last one you saw, which was 520 megapixels, 3.2 gigapixels. And if it's easier, we can go to the slide first. Okay. Okay.
Our software, live software sometimes crashes.
All good. I'm going to tell you about the survey and the camera, and we'll look at it when we get a chance. Okay, so this is it's called the Vera Rubin Observatory, and the camera on this observatory is called the LSST camera. It's going to do something called the Large Survey of Space and Time. There are a couple of amazing things about this telescope. Actually, the camera itself is still very nearby. It's being completed at SLAC in Menlo Park. So I saw it just a few days ago. It's a beautiful camera. And this camera is going to ship down to Chile in June. And it's going to do a 10-year survey of the sky. So this 10-year survey of the sky, it's basically going to observe half the sky every 3 nights. So, let's see. We got it? Yeah, let's go for it. All right, here's the telescope on a mountain in Chile. This is the telescope itself, and actually the camera, which is about as big as a car, is in that little enclosure Right there, it's like that yellow thing that you see there. That's the camera. So is that the end of the video? Okay, then let's go to the camera thing. Okay, that's a picture of the camera. This is, as I said, in a clean room in Menlo Park still, but it will be shipping down to meet its telescope home in a few months. So this 3.2 gigapixel camera, largest camera ever built, what's beautiful about it is that it can see very deep, and it also has a very wide field of view. So that camera that you see on the left, those CCDs will project onto a very large patch of sky, about 40 times bigger than the full moon. And that will enable it to survey the entire southern sky every 3 nights. And that means over a 10-year period, it will take about 825 images of every patch of sky. So that will allow us to do 2 things. The first is it will allow us to stack those 800 images and make a very, very deep image. But the second thing is that it will actually allow us to take a movie of each patch of sky. So this is a totally new way of doing astronomy. Every night we're going to have 1 million alerts of things that changed, things that were different than the last time the telescope looked at it. And that will include everything from asteroids very nearby to stars in the Milky Way that move, to supernova that get brighter when they explode, to anything else that goes bump in the night. Just to give you a sense, just each individual image is also going to be spectacular. So let's just look at that galaxy image. This is kind of this is just a nearby galaxy from the kind of the precursor survey, the Sloan Digital Sky Survey. And there's a smaller telescope. Let's go to the next one. This is like close to a single image from LSST is going to look something like this. And now imagine that we do this 800 times and get deeper and deeper every time. So that's the kind of image that we're going to have of the universe. Coming back to what we talked about before with these tiny, tiny galaxies, I told you we know about 60 of them right now. I'm expecting that in the first year of data from LSST, we're going to find 100 more. And that's going to teach us a tremendous amount about, at a minimum, what dark matter isn't. I don't know yet whether it will tell us what dark matter is. Okay, so I'm almost done. I just want to say a few more words about new ways to look for dark matter. So one thing is we'd like to see dark matter on Earth in a detector. And so these are some of the new experiments that people are building. Much, much bigger experiments underground. Actually, this LZ one that's pictured on the right just started taking data this year and already has limits on dark matter that are about a factor of 10 stronger than the limits that we had before. The one in the middle, one of my colleagues is working on this really cool project called Dark Matter Radio. It's called Dark Matter Radio because it's kind of like an AM radio where you tune the frequency that you're looking for the dark matter signal, and then you see whether it's there. And this is looking for axion dark matter using a big magnet. Next slide. We not only want to look on Earth, we want to look in the sky. And I think the next 2 decades in astronomy are just going to be incredible for dark matter and everything else that we look at because of the next generation of instruments that are coming. So JWST, you heard about, LSST, also things in the radio. We have several other space telescopes coming. Next generation space telescope called the Roman Space Telescope is kind of like a successor to Hubble, except for its field of view is 100 times larger than Hubble. And then we have a next generation of very large telescopes on the ground called the GMT, TMT, and ELT, which are going to be able to take just incredibly deep spectra of all of these things and provide new ways for looking for dark matter. So I'll just end on this final set of images. Remind you that some of the tools that we have to look for dark matter, we can make spectacularly accurate maps of where dark matter is in the universe. That's what you see on the right-hand side. We can look for how dark matter curves space-time through gravitational lensing. That's what you see in the middle. And we can use the tiniest galaxies in the universe, which really appear to be dominated by dark matter and not stars, to actually learn more about the speed at which dark matter moves and how it might interact with itself or with normal matter. So I will leave it there and take questions.
Thank you very much. I'm going to give Dr. Wechsler a moment to get back down to the front of the stage. I will note that if you absolutely need to leave the theater, you can exit either at the top of the stairs or at the bottom. If you're sticking around for Q&A, if you have a question, please raise your hand, Bing, or I will come to you with a microphone so that you can use it and everyone can hear your question. So please, you'll raise your question. And looks like fifth row near the center.
Hi, thanks so much for the talk. This is maybe a basic question, but can you tell us a little bit more about how you can actually understand the depth of different objects that this kind of imaging is seeing?
Yes, that's a great question. Okay, so question is, how can we understand how far away something is, right? We see an image on the sky. That only tells us where it is on the sky. The basic answer is that we can look at its colors. And the idea is, so some of you may have heard of something called redshift, which is essentially the fact that because we live in an expanding universe, the further a galaxy is away from us, the faster it is moving away from us. And because it's moving away faster, all of its light will be shifted to redder wavelengths than if it's not moving. And so if you imagine, it's not exactly true, but if you imagine for a minute that all galaxies at all times are the same, that meaning they have the same amounts of, old stars and new stars, the same amount of oxygen and carbon. If they were all the same, then the only thing that would happen when a galaxy gets further away from you is that its colors would get redder. Now, of course, it's a little bit more complex than that because stars also age, and there's also things like dust and all of these things, so that can confuse the issue, and so we worry a lot about those things, but the basic answer is we look at its colors. Now, the spectroscopic instrument I told you about, the things that actually makes measurements of, dispersing the light as a function of wavelength, that gives you a very precise measurement of where something is. The ones that are just images, it's kind of like a very fuzzy third dimension because it can be easy to get confused between these things. So it's like you have a distance, but it's got a very big error bar.
Next question from the third row.
Okay, thanks. So from what I understand, dark matter is necessary for clumping of matter, right?
Yeah.
Is it a prerequisite then that every galaxy has dark matter?
As far as we know, the answer is yes. So we have not yet seen a galaxy that does not have dark matter, and I personally don't understand how you can form a galaxy without dark matter. People look hard for these things to try to see whether we can find galaxies that don't have dark matter. But my understanding of galaxy formation is that in order for a galaxy to form, you need gas to cool, and that's what enables the stars to form. In order for that gas to cool, you need enough stuff in one place, and that's basically why you need dark matter. And so far, that's what we've seen. Every single galaxy, actually, from the tiniest ones that I told you about to kind of regular ones like the Milky Way to these big galaxy clusters, they all are surrounded by these clumps of dark matter.
So next question is from the third row from the top.
Thank you so much for the talk. I thought it was just going to be slides, but immersive was epic bonus. My question was if you could speak a little bit on some irrefutable evidence other than gravitational lensing that could point that, yeah, this is dark matter, not just some other source of gravity.
Yeah, great. So I didn't list all of the reasons we believe dark matter exists. Actually, the number one in my book has nothing to do with galaxies. The most convincing thing to me is actually the cosmic microwave background. So you saw that image of the very, very early universe, 400,000 years after the Big Bang. We can measure the fluctuations in the temperature at that time extremely precisely. And those fluctuations in the temperature alone, even without anything that comes after, tell us a lot about what the universe is made of. They tell us about the geometry of the universe, so the total amount of matter and energy, and they tell us about the ratio of normal matter to dark matter. And it's a little bit complicated to understand what that measurement is, but actually it's like, I think, 100 sigma measurement of the existence of dark matter, or specifically that the amount of matter in atoms has to be different from the total amount of matter because of these spots. Okay, so that's actually, to me, the most convincing piece of evidence. A second piece of evidence that I think is very compelling, independent of all of the, every single galaxy where we measure these things, is there's a system called the bullet cluster, which is two very massive galaxy clusters crashing into each other. And sometimes people try to explain dark matter away by saying, well, can't I just change the laws of gravity? So yes, you can in a galaxy. If all you want to do is explain galaxy dynamics, you can just mess with the laws of gravity and you can get it just fine. You can't explain the cosmic microwave background with those theories. And what you definitely can't explain with those theories is the idea that dark matter and normal matter would not be in the same place. In these two galaxies that crash together, actually, the gas behaves differently than dark matter. Gas particles, when they hit each other, they cool or they heat, one or the other. Both things can happen. And so when you have two massive galaxy clusters running into each other, the gas is very hot and it shock heats, and it basically kind of stays put, not quite, but compared to the dark matter, it stays put. The dark matter, nothing happens because there's no electromagnetism, there's no friction, basically it keeps going, whereas the gas gets stuck. So that measurement tells you very convincingly that there is stuff different from where the gas is. And that's another pretty compelling piece of evidence for dark matter.
Next is from a gentleman in blue in the middle of row 5. Can you pass this down, please?
Thank you so much for your talk. I really enjoyed it. I just wanted to know if there's any comprehensive comparison between the research that's been done on dark energy compared to the research that's done on dark matter.
When you say, is there any comprehensive comparison, do you mean like, is there something written? Or
No, research...
Are they comparable
Yeah.
in terms of what's been done?
Yeah.
Yeah, I don't know if they're comparable, but let me tell you a little bit about how I see the relationship between these two things. Okay, so I didn't say very much in this talk about dark energy. I also work on dark energy. It's also very interesting. I just decided to focus here. The main thing we know about dark energy is it seems to be a property of space itself. We don't really understand this, but if the universe was only made of matter, matter always attracts other matter. So you got some matter here, you got some matter here, gravity's gonna try to pull them together. That does not appear to be what is happening with the distribution of galaxies in our universe. The distribution of galaxies, they're not just expanding away from each other, they are accelerating. So they are expanding at a faster and faster rate. And that cannot happen in a universe that is only made of matter, because matter is always gonna pull them closer together. So the fact that they are speeding up and not slowing down is telling you that there is something else. We call this something else dark energy. It's not, it's kind of a funny name, and it's not really the same as dark matter is, but my best guess is that it's a property of space itself. So I would say that in terms of the measurements, in both cases, we have a very good measurement of what's happening with dark matter and what's happening with dark energy. We know how much dark energy there is. So far, it appears that it is the same everywhere in space and time. So it seems to be the same 10 billion years ago as it is today, and it seems to be the same over there as it is over here. We don't have any good theories. So one of the reasons I actually like dark matter a little bit better than I like dark energy is because there's so many good ideas for what it might be. I don't know what it is, but there's like 1,000 good ideas, and I can look for one, and I can look for the other, and I can rule one out, and I can see if I find the other. Dark energy, there's like, maybe it's a property of space. We don't really get it. So our best way to look for it is just to see if we can break that theory. So what we're trying to do now is we're trying to see, is it really the same everywhere? So is it really the same over there as it is over here? Or in particular, is it the same 12 billion years ago as it is today? And we are able to make those measurements with higher and higher precision. I'm actually very excited about stuff that we're going to be able to measure in just like a year from now with this instrument I mentioned, DESI, because it's going to have so many spectra that what it will enable you to do is actually two separate measurements. One is measuring the expansion history of the universe, and the other is measuring how fast structure grows. So in those movies, like how fast is that movie proceeding? And by making those measurements separately, general relativity, so our theory of gravity, says that the relationship between the expansion history of the universe and how fast structure grows is predicted by the theory of gravity. So if you measure one, you should be able to predict the other. So now we're going to go measure both of them and see whether they match. And that's essentially doing a measurement of general relativity on the scale of almost the whole universe. And it's pretty cool, and it will be a very good test of dark energy. And I hope something will break. There are actually, I didn't talk about it here today, but there are two puzzles that we have right now in cosmology besides what is the nature of dark matter and dark energy. One is that the cosmic microwave background is sort of measuring how fast the universe is expanding, and we measure how fast the universe is expanding today, and they don't quite match, and we don't know why. The second is that the cosmic microwave background makes a prediction for how clumpy the universe should be today, and we measure it today, and they don't quite match. Like pretty close, but people are getting more and more worried that they are not quite matching, and we don't know why. Look, I hope that something's wrong with with our theories, and that we'll have a surprise. So come back in a few years, and we can talk again.
We have an online question.
Yeah, I have one online question. Jono asks, how do you place two stars in 3D space whose photons are billions of years apart? One of them could be in a different location, assuming it still exists. This hurts my brain.
Okay, it hurts my brain too. How do you put two stars in 3D space? I don't think I quite get it. What was the second part of the question?
One of them could be in a different location. I wonder if they're talking about the lensing, maybe?
Right. Okay, good. That must be, maybe they're talking about the lensing, right? Okay, so this is a pretty crazy thing. Let's imagine that my hand is the gravitational lens and there's a galaxy behind it. What you're seeing in that image is like multiple images from the same galaxy. And the reason is because this clump in the middle actually distorts space-time. And it distorts it in such a way that the path of light that a photon can take, it can actually take two different paths of light which have different lengths, essentially. And that's how you get, that's how you can get these, a photon coming from the same galaxy appearing in two different places in your telescope. I hope that was a partial answer to the question, but it breaks my brain too.
We have another question from the very top row.
Excellent presentation. Thank you very much. Forgive this very pedestrian question. I'm sure
All
you'll
good.
find this out. Early astronomers cured us of the great hubris that we were suffering from, that the Earth is the center of the cosmos. Have we, in 2023, been able to yet identify the center of the cosmos, or where the central, North Pole of the entire
Yeah.
show is at this point?
Here, there, and everywhere. Everywhere is the center of the universe, and nowhere is the center of the universe. So it's kind of strange, but I'm totally serious. So for us, the universe is expanding away from us. And it's, you go over there, it's the further away you go, the further it's expanding away from us. If I lived in a galaxy over there, I would also think that the universe was expanding away from me in the same way that I do over here. And part of the thing that's kind of strange about this expanding universe, we don't really know the answer to the question, what is it expanding into? And we don't even know if it has an edge at all. We don't even know if the universe is finite or infinite. What we know is that there is an edge to the observable universe from us. And the observable universe is like a perfect sphere around us that, if it wasn't expanding, would be 13.8 billion light years away, because that's how long light would have had to travel since the beginning of the universe. It's actually much further, because the universe is expanding. The edge of our observable universe is about 47 billion light years away, because it's gotten farther away since it started expanding. But if I was over there, it would be 47 billion light years away from me. And so yes, everywhere and nowhere.
Next is from the fourth row, left side.
Thank you again. Other than the property of mass and ability to bend space-time, what other properties do we know dark matter has to have, can't have, might have, depending on which flavor it is?
Great. Okay, good. Sorry, I couldn't see you. Okay, so we know how much there is. We know its density in space. We know how it behaves. So we know that it can't, we know some things about the velocities of the particles, because if they were moving very fast, they would destroy those tiny galaxies. We know something about how much it interacts with regular matter. So we know it can't interact very much, because if it interacted very much, we would have seen it already, and it also would change the behavior of some of those tiny galaxies. That's pretty much what we know. I mean, those are the two main things that we're looking for, like the holy grail of what we're looking for. We want to know the mass of the particle, and we want to know how it interacts. We want to know, does it interact with itself? So if I'm a dark matter particle and I run into another dark matter particle, does anything happen? We want to know, does it interact with normal matter? So if I run into a lot of normal matter, does anything happen? And so far, we haven't seen either of these things. It doesn't mean they didn't happen. They don't happen. It just means they don't happen at the rate we've so far been sensitive to. So those are the basic things that we know. And the cool thing is, I think right now, is that we have so many new techniques that are teaching us more every day. So both in the sky and on the ground.
Thank you for the talk. So I had a question. When you showed us the image of the dark matter halos, I felt like the clumps of galaxies which are bigger had bigger halos.
Yes.
So is it like that everywhere, or are there places where there's less matter and more dark matter, and more matter and less dark matter? And
that's a fantastic question, very close to my heart. One of the top things that I try to study is the statistical connection between galaxies and dark matter halos, and whether it is the same everywhere or not. And so to zeroth order, basically, bigger galaxies live in bigger dark matter halos. Everywhere, And, the scatter does not appear to be that large. There is some scatter, right? So a halo that is, similar to the size of the Milky Way, it might have a galaxy that's 50% larger than the Milky Way, but probably not a factor of 3 larger. So, those differences can be due to, for example, how the galaxy assembles itself, whether it got put together early or late, could change the number of stars compared to the amount of dark matter. But it's one of the reasons that I'm really excited about this frontier of pushing to very tiny galaxies is because they have so few stars. And so if we're really able to study what's happening for the tiniest galaxies, we can learn a lot more about exactly your question and what it teaches us about the particle physics properties of what dark matter is.
So we have time for just a couple more questions. Looks like the next one's on the second row.
Second row.
Hi. I'm trying to decide if I'm a dark matter skeptic or not. I'm not a cosmologist, so I don't have the background to get into it. I do know some about science. And I keep thinking of the occasion when they were trying to prove that there was an ether that was the substrate that electromagnetic waves propagated through. So they came up with experiments, and everyone was sure there was an ether.
Yeah.
And the experiments kept coming up nil. So what had to change was the theory, not the idea that they couldn't find this ever elusive ether. You've probably heard this before. So what I'm thinking is why you gave the example of a case where you could tweak the gravitational variables such that you could make certain formation things come out right if you did that, and you didn't need dark matter to explain it. But you couldn't do that for all the cases needed. But on the other hand, you wouldn't expect it to be a tweak if that was what was wrong, because, for example, you can't tweak Newton's theory to get to Einstein's theory.
Kind of can.
Some tweaks there to get relativity in there? Okay. So my question, long-winded question, is I assume there are skeptics still in the community, and what is the response to the question or to the idea that there's actually something wrong with the existing cosmological theories, astronomical theories, and there really is no such thing? It's just that, that's an easy explanation for it.
Yeah, so I guess so I just very briefly comment on Newtonian versus Einstein gravity. Newtonian gravity is a very good approximation to general relativity in most spaces, right? It's a very good approximation. Okay, back to dark matter. Yes, there are some skeptics. I would say the ratio of skeptics to people who think dark matter is a better theory is much higher in the general public than it is among working scientists. So not that many dark matter skeptics who are actively working in this area, although it's not zero. What I would say is that based on what we know now, dark matter is a much, much cleaner explanation for what we see than any alternative that people have come up with. So changing the laws of gravity, it might sound simple because you just get rid of some stuff that you don't know it exists. It doesn't make predictions for all of the things, for many things that I told you about and many things that I didn't tell you about. Those ideas of, so it can predict how a galaxy would rotate. That is something it can predict. It cannot predict the cosmic microwave background. It cannot predict the distribution of galaxies in the universe. So the fact that we've actually measured the positions of these millions of galaxies and how they're distributed, that is a prediction that comes out of my simulations that include dark matter. And no one who has a theory that doesn't include dark matter is able to explain those data. So that's one example. So I guess what I would say is, look, I'll be thrilled if we find another explanation that is better than this one. But right now, this explanation basically explains everything we know about the universe. It's with a new thing. It has a new thing, but it explains what we know. And it makes lots of predictions, which we actually go out and test. Not only that, there are lots of good reasons to believe that those dark matter particles might exist, just from things that have nothing to do with these observations, from particle physics theories that say this particle should be there. And we haven't had the sensitivity to detect it yet. So I don't think it's that weird that we haven't found it yet, because it may be many things that we wouldn't have been sensitive to yet. So it's a partial answer to your question.
And we're just out of time for questions. Thank you again, Dr. Wechsler, for your
Thank you.
time this evening. If you have any further questions, please feel free to come down and ask. Otherwise, again, you can exit at the top of the theater or the bottom of the theater and